Hello, everyone. Today we begin a fascinating chapter called Introduction to Linear Polynomials. Mathematics becomes powerful when it begins to reveal hidden structure inside changing situations. A delivery company packs notebooks into cartons. Each carton contains 6 notebooks. A student buys X cartons, along with 4 extra notebooks kept separately. The total number of notebooks can be written as 6x plus 4. This expression is more than a collection of symbols. 6x and 4 are called terms. The symbol x is the variable, a quantity that can change. The number 6 is the coefficient of x because it determines how strongly the variable contributes to the expression. And 4 is called the constant term because it appears independently without any variable attached to it. Now consider another expression, 12p minus p squared. Just like the previous expression, this expression also contains only one variable. Expressions involving exactly one variable are called univariable polynomials. Uni means one. And once powers of variables begin appearing, mathematics starts classifying these expressions according to their structure. Observe carefully. In x squared plus 4x plus 7, the highest power of the variable is 2. So this is called a polynomial of degree 2. A quadratic polynomial. Now look at 3y cubed plus 2y squared minus 5y plus 8. The highest power here is 3, so this becomes a cubic polynomial. And when the highest power is exactly 1, the polynomial is called linear. For example, 5m minus 9. The highest power of m is 1, so this is a linear polynomial. Linear polynomials describe situations where quantities change uniformly. Imagine a music club charging a registration fee of 300 rupees and an additional 40 rupees for every workshop attended. If a student attends W workshops, the total amount becomes 300 plus 40W. Now pause for a moment. If a student paid 780 rupees in total, how many workshops were attended? We form the equation 300 plus 40W equals 780. Subtracting 300 gives 40W equals 480, so W equals 12. The student attended 12 workshops. Notice how algebra transforms a real situation into a logical structure. Unknown quantities become solvable because relationships become equations. Now, linear polynomials begin behaving like machines. Suppose the rule is 3x plus 2. If the input is 5, the output becomes 17. If the input is -2, the output becomes -4. Every input passes through the same mathematical rule and produces a predictable output. This is the beginning of functional thinking. Now the chapter moves into patterns. Observe a growing arrangement of square tiles. Stage 1 contains 2 tiles. Stage 2 contains 5 tiles. Stage 3 contains 8 tiles. Pause and examine the pattern carefully. What remains constant? Each stage increases by exactly 3 tiles. That constant difference is the signature of a linear pattern. Now, mathematics asks a deeper question. Can we determine the number of tiles in the 100th stage directly? To answer that, we construct a rule. Since the pattern grows by 3 at every stage, the expression must involve 3n, where n represents the stage number. But when n equals 1, the expression 3n gives only 3, while the actual first stage contains 2 tiles. So the expression is exceeding the pattern by 1. That adjustment gives 3n minus 1. Now verify it mentally. For stage 4, 3 times 4 minus 1 equals 11. For stage 10, 3 times 10 minus 1 equals 29. A single expression now controls the entire infinite pattern. This is mathematical generalization. Now the chapter moves toward linear growth and linear decay. Suppose the cost of renting a bicycle starts at 80 rupees and increases by 25 rupees every hour. The total cost after h hours becomes 80 plus 25h. As time increases, the amount rises steadily. This is linear growth. Now consider the reverse situation. A water cooler initially contains 40 liters of water, but loses 3 liters every hour. The amount remaining after t hours becomes 40 minus 3t. The quantity now decreases uniformly. This is linear decay. Growth creates rising patterns. Decay creates falling patterns. And when these relationships are plotted on a coordinate plane, something remarkable appears: straight lines. Every linear relationship can be written in the elegant form y equals ax plus b. This equation contains the geometry of constant change. The number a controls the slope, how steeply the line rises or falls. The number b controls the y-intercept, the point where the line crosses the y-axis. When the slope is positive, the graph rises from left to right. When the slope is negative, the graph falls. And when two lines share the same slope but different intercepts, they remain perfectly parallel. A straight line, therefore, is not merely a geometric object. It is the visual signature of uniform change. By now, algebra should no longer feel like disconnected formulas. Expressions, equations, patterns, functions, growth, decay, and graphs are all connected through one central mathematical idea: constant change. And once that idea becomes clear, solving problems becomes less about memorization and more about recognizing structure. Now think carefully about this final question. If two straight lines have exactly the same slope but different y-intercepts, will they ever meet? Pause. They will never intersect. Because equal slopes mean equal steepness. Both lines rise or fall at exactly the same rate forever. Their separation remains constant at every point, and that is why lines with equal slopes are parallel.